Today, with Thomas's Calculus, 14th edition. In this book, Chapter 3, Derivatives, Chapter 3.7, Implicit Differentiation. You can read the theory in this book. We will solve dy over dx when y square equals x. Open up Visual Studio Code, CPP 17 2023 parallel. Select empty space, new folder 160, Implicit Differentiation. Click this button, implicit.cpp, hit enter, Ctrl B. Author Thomas Kim. First edit December 11th, 2022. To follow my current video, I assume you have watched my previous videos listed here. In episode 50, I explained mathematical theory behind numerical derivatives. In episode 151, we implemented numerical derivatives using 7-point stencil algorithm. In episode 152, we implemented numerical partial derivatives. In episode 153, we implemented parameterized derivative using chain rule. Include CPG, SED, extensions include CPG, Calculus, namespace, CNA, CPG, Numerical Analysis, namespace, CPG, types. I will close this file, then arrange side by side like this. This example is from Thomas's Calculus, Chapter 3.7, Implicit Differentiation. Example 1, page 149. Page 149. This is function header. In the main, copy this function header and paste it here. In this document, we have to solve x and y. This problem first. It belongs to nonlinear equation. To solve nonlinear equation, we need matrix. Matrix belongs to linear algebra. I already implemented solving nonlinear equations an year or so ago. We suppose we solved this problem. Here, order f. We take order x, order y. This equation y cube equals x will be represented f xy equals x minus y square. So here return x minus y square. Don't miss semicolon. Or dy over dx positive 1. CNA implicit derivative. We pass 1. It means variable x's position is 0. Variable y's position is 1. So this 1 represents variable y. It instructs compute dy over dx. Okay, y represent compute dy over dx. Then we pass function f at point x is 0, y is 0. Okay, or I can give a line break. At x is 1, when x is 1, y can be positive 1 or negative 1. Copy, paste. Now, negative 1. When x is 1, y is negative 1. Now, LCD, Cout, dy over dx, positive 1. We copy this, paste, CPG, and there. Copy, paste, negative 1, negative 1, CPG, and there. Or we can say copy, paste, STD, Cout, STD, CPG, and L. So I created a simple function. We can use any compiler. I'll be using Microsoft compiler. CD 160 Implicit Differentiation CL EHSC STD C++20 Implicit.cpp fe m.exe, hit enter. CLSM. It means at point 1, 1. This represents point x coordinate, y coordinate. The slope is 0.5. At point 1.0, negative 1.0, the slope is negative 0.5. As you can see, when x is 1, the slope is 1/2 or 0.5. In this case, when x is negative, the slope is negative 1/2 or negative 1.5. So we solved this problem using implicit derivatives. If you think this problem is too simple, then we can try another example. Now we are given circle radius 5. In figure 3.29, this is circle radius 5. We want to evaluate slope at point 3, negative 4. We will solve example 2 function name. So copy this function name, paste it here. In this case, we are given circle. This is circle x squared plus y squared 25. It can be represented fxy equals x squared plus y squared minus 25 or f or x or y. Return this expression x times x, y times y, semicolon, semicolon, or dy over dx, CNA, implicit derivative. We need to instruct the position of y. 0 is for x, 1 is for y. So we pass 1. I will give a line break. We want to evaluate at point 3, negative 4. So we pass f 3.0, negative 4.0. STD, Cout, dy over dx, dy over dx, CPG, and L. Here, STD, Cout, copy the function name, paste, CPG, and L. Now, we will build again. CLSM. So in this case, the slope is 0.75. So 3 over 4 is 0.75. this is accurate. If you are doubt, you can try this. 3.0 over 4.0. Let's try it. We rebuild CLSM. So it's correct. Now we will solve more advanced real application. In this book, if you scroll down in chapter 14, partial derivative, section 14.4, the chain rule. If you scroll down in page 826, you can find the algorithm behind implicit derivative. This algorithm is implemented using this theory explained here. Implicit differentiation revisited. If you scroll down, you can find Theorem 8, a formula for implicit differentiation. Basically, I implemented implicit derivative using the explanation here. Now we will solve much more advanced and complex problem. Example 6 in page 827. So I will copy and paste the function header. Test implicit differentiation. Example 6. Paste it here. SED, cout. I will copy the function name, paste it here. CPG and L. Now we want to solve dz over dx, dz over dy at point 0, 0, 0. If f is given like this, copy, or paste it here. F now takes three variables, or x, or y, or z. It is x cube, z square, y times e power x times z, z times cosine y. Copy this. Return, paste. It should be x times x, z times z. It should be SED, EXP, x times z, SED, cosine y, semicolon. I will give carriage return. So x cube, z square, y times e to the xy, y times e to the xy, g times cosine y, g times cosine y. Don't miss semicolon. Now, or dz over dx. Okay, dz over dx. Then dz over dy. So dz over dy. CNA, I will give line break here. Implicit derivative. Now we have to evaluate dz over dx, dz over dy. We have to give position of z. 0, 1, 2. So 2. Position of z is 2. Now we pass function f. Then point. It should be 0.0, 0.0, 0.0. Semicolon. SED, cout, dz over dx, dz over dx, SED, CPG, and L. Copy, paste, dz over dy, dz over dy, and L. So we will solve this problem. We already pasted. We rebuild CLSM. Wow. 0, -1. Scroll down. You can find dz over dx 0, dz over dy -1. Our solution is perfect. You probably see this book, a book for calculus, a book of mathematics, but I have different eyes from yours. I see this book, a book of computer algorithm. Now, in chapter 14, chain rule, we will solve problem 35, 37, etc. We can basically solve all the problems in this book, not only in this chapter. We can solve all the problems in this book. We will have 3 minutes coffee break. Finding partial derivatives at specified points. We will solve problem 35, then problem 37. Basically, we can solve all the problems in this book. Actually, we can solve more advanced problems than in this book. If you are doubt, keep watching. I will copy this message. Thomas's Calculus, 14th edition, chapter 14.5, the chain rule, exercise 14.4, problem 35. Problem 35, this problem, page 829, 829. This is the function name, std, cout, copy this function name, cpg, and L. Now we want to find dw over dr. W is defined like this. Square or W, we need 3 variable or x or y or z, semicolon. Return, I say or s, x plus y plus z, s times s. So we defined function w here. Now function w takes 3 variables x, y, z. x, y, z is described here. Or x or R or S. Return R minus X. This is function X or variable X. I will copy, paste it here. Now, or Y, or R, or S. This is our function for Y. Return SED cosine R plus S. Don't miss semicolon. Or Z, or R, or S. Semicolon. We define G like this. Return SED sine R plus S. So we defined here function W, then variable X. X is a function of R and S. Variable Y is a function of R and S, defined like this. So is Z. Z is a function that takes two variables, R and S, and defined to be sine R plus S. Now we need to create command CNA create command. We want to differentiate with respect to R. Then we can say D0, 1. 1 means differentiate once with respect to R or 0. In this case, the position of R is 0. The position of S is 1. Okay? 0 represent differentiate with respect to R once. Now D1, 1. It means differentiate with respect to S once. First order partial derivative. First order partial derivative for R. First order partial derivative for S. 1 and 1 represent first order. 0 represent first variable, independent variable or parameterized variable R. This one represent variable S. With this command, or dw dr, dw ds, CNA parametric derivative. We pass command, then our main function W, then SED tuple our variable for function W, X, Y, Z. Okay, please understand, X, Y, Z, these are function itself. Then we pass, it says R is 1. So 1.0 is the value of R. S is -1, -1.0. We defined parametric derivative. Here it is defined cpg calculus.hpp. Sadly, this implementation does not work for Microsoft compiler as of today. If you use Microsoft compiler, you will have not yet supported message. However, you can use for GNU, G++, Clang, DBC++ compiler this very short and elegant function solves almost all parametric derivative. Once again, This function is very compact but can solve almost all, actually all parametric derivative. Now SED Cout dw over dr dw over dr cpz and there copy paste dw over ds dw over ds. Now copy this function name, paste it here, semicolon. I will use cpz and L. If you try it with Microsoft compiler, no matching overloaded function found. Sorry, I made a mistake here. We need to declare using namespace cpz numerical analysis sys rebuild. If you scroll up, you will see static assert failed, not yet supported. This is not the problem of my source code. There is slight problem in Microsoft compiler as of today. I expect this problem will be fixed very soon in Microsoft compiler. Now we will be using Clang or GNU compiler, Clang++, SED, C++20, Implicit.cpp, LTBB12, or C.exe. Okay, it built C. Wow, the answer is 12 and 0 respectively. You can check the answer here is 12. Okay, the answer is 12 because this problem asks us dwdr is 12. Now back to our problem 37. I will copy the header of the problem or function. Copy this, paste it here. This is problem 39. I will solve this problem. We can solve any problem. Page 829. 829. We are given u z. Z is defined 5 times arctangent x. So, although z takes a single variable x. The reason I'm going to solve this problem is it is more complex than other problems. Return 5 times SED arctangent x semicolon. It represents arctangent. Okay, arctangent x. Now x is defined like this: e to the power of u, then ln v, natural log v. Okay, although x, although u, although v. Return SED exp u plus SED log b. Please understand, this log is natural log ln b, semicolon. Now we create auto command. Sorry, I forgot to introduce the namespace. Paste it here. SED cout, copy this function name, paste it here, cpz and L. Now we need to create command CNA create comment. Once again, with respect to u, d underscore 0, we differentiate once. Okay, of course, we can use double differentiation. If we use this command, it becomes differentiate this x with respect to u twice, derivative of second order. Okay, so I will make it 1. d 1, 1. Now, auto dz du, dz dv, CNA parametric derivative. We pass command. Then our function is z. In this case, z is 5 times arctangent x. So z. This z takes tuple x. X is function. Then it says u is ln 2. So SED log 2.0. The value of u ln 2 means SED log 2.0. Then v is 1. So 1.0. SED cout dz du dz du cpz and there copy paste dz dv dz dv and we created this function. Copy paste it. We already pasted. We can rebuild CLSC. The answer is 2, 1. dz over du is 2. dz over dv is 1. This is correct answer of this problem. If you doubt, you can check your answer. 39 dz over du is 2. dz over dv is 1. 2, 1. I said, or I claimed, we can solve all the problems in this book and more. We can solve more advanced problems than described in this book.